All right, let's get started. This is Julianne. I'm with ProSoft, and I'm happy that you joined. Thank you for joining to talk about edge computing. First thing I'm going to mention is we will share this presentation with you along with a copy of the recording. So check for that in your inbox later on. And also, I'm going to direct your attention to the question and answer box. If you can post your questions in there, we will get to it at the end. And that would be great if we get some good questions coming in. So with that, I'm going to introduce Vishal Prakash. He's a product manager here at ProSoft. He's responsible for IoT solutions and industrial protocols like DNP3. So let's go ahead and pass the mic over to him, Vishal.
Thanks, Julie. I hope everybody can hear me. Julie, are you able to hear me clearly?
Yep, I can hear you fine.
Perfect. So welcome again, and thank you for your time. And trust all of you are keeping well and keeping safe. Okay, so we do have a packed agenda. So let's get to the edge and start talking about this. Okay, edge computing is no longer a buzzword. According to IDC, so it's another market research firm, customers are investing in edge computing capabilities today. The report indicates that some 40% of organizations that they spoke to plan to invest in edge technology and solutions within the next 12 months. So we're talking short term. And realizing the benefits of edge computing is becoming a strategic initiative for many of the organizations. And the KPIs that they're focusing on as they make this investment is around better security, especially data security, and we'll cover that, increased compliance, better uptime, and performance. And as customers are making this investment, they're looking at both the short-term and the long-term benefits of the edge computing solutions. And some of the short-term benefits include compliance to data security, like I mentioned, and then reliability, which obviously has got a net positive impact on productivity. Now, some of the potential long-term benefits of edge computing include revenue streams. So again, it depends on the kind of customer. Let's say for you or a machine builder or systems integrator, edge solutions can potentially give you this new revenue stream in terms of increased analysis, additional service. But also customers are looking for reducing their total cost of operations. And when we look at the benefits later on in this presentation, we'll understand how edge computing can help bring down the total cost of operations. So for all of those attendees who are in sales, as my sales colleagues, again, thank you for your time. I know how valuable it is. You won't be disappointed because according to a report from STP Partners, the edge computing solution, so that's both hardware and software, is expected to grow to over 500 billion within the next decade. So considering where we are today, it's pretty insignificant. That's a very, very nice CAGR over this period. And all arrows are pointing towards that, given all of the investments around these technologies. But so, now that I've said that it's no longer a buzzword and there's some real action happening on this, what is edge computing? And before I can get to that to explain what edge computing is, I wanted to take a couple of minutes to explain what the automation architecture today looks like. Today, many of these systems, many of the automation systems, they can be defined or they can be explained using this automation pyramid. This automation pyramid itself, it's a pretty well-known concept, and there is a lot of information out there about how this works and the reason why this particular pyramid was kind of created to explain existing systems. So the base of this pyramid, which is also called the field level or the flow level, so that's the factory flow, is where all the field devices reside. Some examples of these, sensors, actuators, transmitters. So, fundamentally electromechanical devices that tend to do the physical work, so the actual data acquisition, the actual signal, and then they transmit that information to the next layer in this triangle, which is a control layer. The connection between the field and the control is predominantly wired. There is some wireless, but it's predominantly wired. And these field devices that I spoke about, sensors and so forth, they have very specific tasks and they're pretty singular as well. So they're designed with a single purpose in mind. So if it's a flow meter, it's measuring flow. If it's a temperature sensor, it's measuring temperature. They're not multi-purpose devices. And this next layer in the triangle, so that's called the control level, like I said. And this is where all of your controllers, HMIs, protocol translators, gateways, they all reside here. And the devices in this layer, they're all pretty smart. They're very powerful and they can handle multiple tasks. So remember I said at the field level, they're very singular, whereas in this next level, they can handle multiple tasks. So things like reading IO, the ability to translate data, protocol data, taking the field signal coming in and converting that to information that could be understood by the controller, perform complex calculations, things like PID loop control, or even manage entire processes like batch process and so forth. So these devices, they understand the information that's coming in from these field instruments. They're able to translate that information and then act upon that information. Now, the third block in this triangle is the supervisory and the planning block. So this is made up of SCADA software, MES or manufacturing execution systems, historians to store data, and then actual data storage itself, and then of course reporting as well. SCADA, which stands for supervisory control and data acquisition, basically takes the data from the controller or the control level, so from fundamentally PLCs or RTUs, and then it translates that data into a format that can be easily understood by humans. So predominantly in a graphical format, but it also shows all of the data as well. The SCADA can then take that data that it's received and translated from the PLCs, and it's able to then share that information or send that information to historians, reporting packages, and also to the MES systems as well. And MES, which I said is manufacturing execution systems, they are there to monitor the entire plant. And typically they're used by the operations management to understand current status and then operate their plant efficiently and effectively. And this last block right at the top, so that triangle is occupied by ERP or enterprise resource planning systems. Typically, ERP is sort of multiple applications together. So it's a suite of software applications, and it's designed for one level above operations for the top management. The idea behind ERP is that it gives a complete view, not just on the factory floor, but for the entire business. So it does include information like finance and HR and purchasing and all of that. So the idea is now the management has got a complete picture from which they can make the right decisions to positively impact the business. Now, the key to remember in this entire architecture is that the hardware and software components, so your applications and the hardware components that run those applications, they're very tightly coupled. What do I mean by this? At every layer within the triangle, the hardware and the software part of that solution, they're very tightly integrated, very tightly coupled. So for example, if you look at PLCs, they're designed for process control. They're not designed to store data, for example. So it's a very specific purpose. HMIs, on the other hand, are designed to display data from the PLC. Gateways, they can translate industrial protocols, but they're not necessarily designed to do process control. So, which is why I say that the hardware and the application platform are very tightly coupled together. That's something to remember, because when we talk about edge computing, you will see why this coupling, why I'm stressing on this coupling of the hardware and the application makes sense. So, we've kind of spoken about this. This is a system that exists today. It's very popular. It's there in a lot of businesses. It's very, very common. So if this is working and this is there, why should we be talking about edge? What are the benefits? And really to understand, before we can get to that point about why and what, we need to know what the definition of edge is. And this is what this slide deals with. So at a very, very high level, edge computing is the deployment of intelligent devices at industrial sites for distributed real-time analysis of data close to the source of that data. So there's a lot in that statement. Let me repeat that again. And that's a very simplified version of the edge definition. So again, edge computing is a deployment of intelligent devices at industrial sites for distributed real-time analysis of data close to the source of that data. And I think that's very important to remember, right? So obviously with edge computing, there's more than just a definition, and like I said, I've drilled it down to a fairly simplistic definition. There's a bit more to that. There is in fact also multiple types of edges as well. And the location of the edge computing device and the resources that that device has got in terms of processing power determines the type of edge. And so this is a table actually from a company called IoT Analytics. So again, they're a market research firm. This, I think, captures the essence of the different types of edges and the characteristics pretty well. So there are three types of edges, thick, thin, and micro. And what differentiates these three different types of edges are the compute resources and the proximity of the device to the data source, and also the latency as well. So for example, if you look at the micro edge, which is pretty much on the factory floor level, the distance there in terms of the edge compute device to the actual data source is really in meters, and we're talking single digits, so very close. But also the information is real time, so your latency is very, very low, typically less than a millisecond in most cases. And then another example, if you look at networking equipment, they're part of the thin edge. Here, networking edge devices are located close to the data source again. So if you think about networking equipment, they connect PLCs to other devices like drives and other things. And so that equipment sits pretty close. People tend to minimize the amount of cable run that there is. That also helps in reducing the latency as well. So this is sort of edge broadly, the three types. There is also the cloud, which is also a type of edge computing. Now, the difference between cloud computing and edge computing is that cloud computing is more centralized, whereas edge is more decentralized. And because cloud is more centralized, it's got a lot more compute power, a lot more storage, but it also means that it cannot be everywhere. So you've got these localized and regional and sort of national data centers where everybody wants to send in information for processing, which means the distance between the device, the edge compute device of these data centers and the data is pretty significant, talking several kilometers. And then there's also higher latency as well. So we're talking generally in the seconds is where the latency comes in. Edge computing devices, on the other hand, they have very little latency because they're so close to the source, and they also save on bandwidth because they're able to analyze this data locally. Okay, so what's driving this edge evolution? It's not a revolution, it's just an evolution to where we are, to where we are heading towards. And what I wanted to look at was the factors that's driving this evolution from an industrial automation application perspective. So if you remember this slide, I had this up a couple of slides ago. The only difference is that the arrows are pointing inwards rather than outwards. And I'd stated that the hardware, software, and the solution, so the application and the hardware, they were very tightly coupled. So that was this existing automation pyramid model where the applications and hardware, like I said, were very tightly coupled. So, and the push towards this edge computing is really because of one word, and that one word is decoupling. So what do I mean by that? So with the rise of cloud computing, remember, which I said is another edge computing case, and advances in certain technologies meant that tightly coupled industrial applications they could be decoupled from the hardware they need to operate on today. And what made this possible was the technologies that I've listed there in the slide, and I'll go through each one of them fairly quickly. So the first one is containers and microservices. Containers, think about that, it's a unit of software that has everything it needs to execute. So typically, a piece of software has got like an operating system, and then it's got several dependencies. The idea with the container is that you put everything in one block, in one piece of code, so it's got everything that it needs to execute. Microservices, they can contain multiple containers, and they run as an independent service. So what containers and microservices do in this architecture is they provide resiliency, scalability, independence, portability, and agility. And that's a lot to take in. So a simple way to understand what these containers and microservices is, I think of a shipping port. You know, there are a number of tasks in a shipping port, right? And they're all independent of each other. Like, for example, the ship coming into dock, then you've got the onloading or the offloading of the containers itself. Then you've got the independent movement of cranes. And then you've got moving those boxes once you're offloaded of the ship to other parts within the port. From there, they are then loaded on to trucks or other things to be sent out. So even though these tasks are all intertwined, but like the failure of one task does not affect the operation of another. So for example, if you think about it, if there's one crane that fails for whatever reason, there's always another crane that can take its position and still offload the containers from the ship. So that's exactly where the containers come in. So it's sort of completely self-contained, everything in one to execute. And when you've got multiple containers, the idea is if one fails and the other can take over. So you've got this very high reliability in that process. The next piece of technology that's enabling this edge evolution is open source libraries. Again, as the name suggests, this is software that can be reused, modified, or published without additional permissions. So fundamentally, what that means is you're not reinventing the wheel every time you want to do. So where that's very helpful in edge computing is that the amount of time required to develop an application, or the time to market, or the time to test something is significantly reduced. The next one is connectivity. And here we're talking about both wired and wireless. So wireless has become pretty ubiquitous. You just think about what's happened to just our cellular technology, the way we use it over the last 10 years, right? It's becoming increasingly reliable. It's present everywhere. And in fact, cellular coverage is actually the second most abundant thing available on Earth other than the air we breathe. I heard that in a TED Talk some months ago. So that's pretty fascinating. And that entire, that change in cellular technology, it's ubiquitous, really only happened sort of over the last decade, 10, 12 years or so. Now, there's also been some pretty significant improvements in wire technologies as well. So you've got things like plant-wide Ethernet and time TSN, and then single-pair Ethernet. So all of these technologies mean, and as the number of devices are starting to increase, it means that more and more of these devices can be connected into a network. So that clearly increases the amount of data that has to be transmitted, processed. But with these technologies, it ensures that the right data is being sent to the right place with minimum latency to ensure that these processes continue to operate efficiently. So cloud computing, I spoke about that earlier. Again, cloud computing is centralized compared to edge, but what it offers is almost unlimited processing power and storage capabilities. There is a limit, but for practical purposes, you can say that it's something that's very off. So the advances in that technologies and the solutions or the process that we use to create the success in cloud has kind of walked its way down to edge computing. And then, of course, edge computing power as well. Again, I mean, I don't have to say much about it. We just see how these devices are getting smaller, cheaper, and better every day. So as a result of this change and these adoption of these newer technologies in industrial automation, that pyramid that we spoke about a couple of slides ago, that's evolving as well. And that pyramid is evolving to become more of an automation pillar. So again, go back to that decoupling. So the decoupling of the hardware and the application, again, thanks to the advances in the technologies that I just mentioned, this pyramid is becoming more of a pillar. So not so much a flat structure. You can certainly look at this, but it is, I thought I was running out of time, sorry about that. But it is certainly more refined compared to the pyramid. So in the pyramid model, you've got the separation of the functional layers from the factory floor up to the management systems at the top. Real-time communications is really just between the field and the control level where the sensors are located. But with the other systems, it is not quite real-time communication. The automation pillar in the industrial environment still has that field level, right? So that does not change, except now you've got a lot more devices. So all of the field devices have in fact become a lot smarter. So whether you're talking sensors or transmitters, they've all become very smart, and they provide or they produce copious amounts of information, diagnostic information, information about the health of the sensor. And all of that information is super useful in trying to do things like predictive maintenance, in ensuring increased efficiency. So all of those metrics, if you want to improve on those, data is required, and these new devices can provide that. So with that increased, with those increased number of field devices, they're smarter and they allow for this analysis and control of the manufacturing functions. Now, the biggest change between the pyramid and the pillar is actually in the control level, where the functions have tended to become more distributed. Functions like safety and fast processes benefit from this change because they are now closer to the source of where the action, like if it has to detect a safety valve failing, you've now got processes in place where that detection can happen significantly quicker than what it used to happen in the past. And then some of the less critical PLC functions, they can become more centralized, still locally, but they can become more centralized. And by doing that, they add flexibility as a process can be removed or added based on demand. So, for example, think of a manufacturer that has to deal with, orders during the holiday season. And with the pyramid model, he would need to have dedicated resources to deal with that uptick. And then once he's dealt with that, those resources tend to stay idle. You cannot use them the remainder of the year because you're not producing as much of the goods. And the idea with the pillar model is that you don't need to do that. When there is an uptick in orders, when you've got to, to deal with that holiday season, you can dynamically reallocate the right resources to cater for that increased demand. And then once you pass that season, you can then start to reuse those resources for other things within the industrial automation system. So between the field level and the factory backbone, the connectivity level, both the field level and the connectivity it requires this high speed and low latency network. And again, with the advances in the connectivity technologies that I spoke about earlier, makes that possible. Another example of this decoupling, which is driving this evolution, is at the top of the triangle as well, between the MES, SCADA, and the ERP systems. Previously, the ERP used to send information through to the MES and the SCADA to do things. The SCADA used to provide information to the MES. So it was not so much one way, but it was kind of one telling the other what to do. Each had its own dedicated resources. And with the advances in these technologies, the need to have those dedicated resources for each one of those processes is no longer required. So for example, SCADA systems are increasingly moving to the cloud where it can be accessed anytime, anywhere, and on any device. And that better connectivity means that, and the increased compute power means that the field devices can access that information quickly, but then they can also analyze more of that information locally and only sending what's required to the top end. So with all of these changes, again, this kind of transformation from the pyramid to the pillar, what that does is it increases or it reduces data discrepancy. So it actually increases data integrity and increases reliability as well. And this additional power that's now available means that data can be processed more quickly, which should lead to more productivity and efficiency gains. So what are the benefits of edge computing? I looked at 3 different applications. One was an offshore oil rig, the other was a remote pumping station, and the third was a smart factory, sort of a modern automotive factory. And as I went through these use cases and tried to see how edge computing could be useful, what I realized was that the benefits across the 3 were very similar. I mean, all of these applications themselves, they're going through a pretty significant transformation in terms of the field equipment. They're all getting smarter, which means they're all producing more data. So if you look at then from that perspective, the benefits across each of these applications can all be they're all very similar. So the first one is reduced latency. Now, with the right edge compute device, latency can be in milliseconds and sometimes sub-milliseconds as well, like less than a millisecond. I think the biggest beneficiary of this is in safety systems, where now you have the ability to process that data very close to the source and then act upon it, thereby reducing the latency and also the time to act. The next one is resiliency with edge computing. Even though it's ironic, even though we spoke about this connectivity being more reliable and being faster and quicker, edge computing actually increases the resiliency of the system, because with this ability to process data locally and act upon it, you're now not having to be always connected to a centralized system. And even if the centralized system, for example, was to break down or fail, the cloud data center was to go away, the local processes can continue to operate correctly and effectively while you try and recover this communication system. In fact, this is a requirement, let's say, for all of the utilities in Australia, where they needed to have sort of a disaster recovery center that could, even if the system fails, the master fails, the entire system could continue to operate independently. You've got interoperability between old and new technologies, and then security. And especially with security here, I'm talking about data security, because by running these analytics at the edge, users can cut down the amount of data that they have to send to the top end. So here, you're able to better protect your proprietary data, where you're not having to send everything up to a top end. And it's also better than the automation pyramid, because we know that a lot of the security breaches that have happened has been at that SCADA or at that MES level. So now by really analyzing all of the data at that local level, you're having that protection as well. And then remote access, that can be localized to a machine cell rather than like an entire network, for example. And the other benefit is reduced hardware footprint. So as these edge compute devices are, relying on these technologies like containers and microservices and virtualization, what's happening is that they're able to run more applications. And again, because of that compute power, that increased compute, the multi-core processors and all of that, they're able to do a lot more with just a little bit of hardware. So that means now you don't have the need for dedicated devices to do every single thing. You can combine more into one, thereby reducing your hardware footprint, which should then also help you reduce your total cost of operations. So what should be your top considerations as you consider edge compute to help you improve your productivity, your efficiency, your security, and all of those things. I came up with three main considerations. I think the most important thing, the first one is really to define the use case. And this is very important because if you don't define the right use case and getting into the specifics of it, it's very easy to veer away from the aim and then not be able to ensure that the project is completed successfully and that the objectives are met. So, identify the right use case, and then within that, identify the right type of edge for the application. It's also important to understand that with edge computing, IT and OT get even closer. We've already spoken about, and I did a webinar earlier last year about IT-OT convergence. That's continuing to happen. That's continuing to drive the industry forward. So it is very important to ensure that both IT and OT is involved in defining this use case. Because if you look at, again, edge computing, there is a lot to it, right? There's connectivity, there's processing and stuff. And while OT might understand the process very well, IT does bring certain skill set that will help you, again, ensure that this project is successful. And then it's also important to set realistic goals. I mean, there's no point saying that with edge compute, I'm going to increase my efficiency by 100%. It's very important to take baby steps, step goal approach, but it's also important to ensure that as you keep meeting those goals, you're not going back. So that's important as well. I think the second consideration for you to think about is getting, I realize I've gone over, I apologize for that, so I am getting to the close of it. Getting the right team together. Education is one of the most important things. It's ensuring that you have the right expertise, and identifying the right partner for you in this journey is very, very important. And then the third consideration is security and accessibility. So here it is about remote access, again, machine remote access versus network access, data security, the connectivity, ensuring that the connectivity is secure and encrypted and all of those things. And then, of course, monitoring of the edge compute device itself to ensure that it's functioning correctly. So in my opinion, these would be the top considerations for you to think about as you're looking at the edge compute journey. So in summary, edge computing is no longer a buzzword. It's sort of one of the key drivers for Industry 4.0 adoption and driving towards the IIoT and all of that. So new technologies, and primarily software technologies, about how code is written and managed, things like microservices and containers and Dockers, virtualization, and sort of these open source libraries. All of these new technologies have enabled the decoupling of applications and hardware in the traditional industrial automation application space. And as a result of that decoupling, the edge computing evolution is becoming possible, where again, the ability to do edge computing means that you're able to analyze data locally. So some of the benefits of adopting edge computing into your application includes reduced latency, increased data security, and then also increased resiliency as well. And then finally, in order to be able to adopt and execute edge solution projects successfully, you've got to define the use case. You've got to be very specific about it, and you have to get the right expertise. So that includes self-education, but also having the right partner with you across that journey to ensure that that project execution is successful. Okay, with that, I'm at the end of my presentation, and I will open it up for questions if we have any.
Okay. Okay, reminder, go ahead and pop your questions in there. Let's see, we have one question we have. Can you please quantify the latency times?
Thank you, that's a good question. Let me go back to that slide. It's up here. So as you can see, latency, real time means it is sort of sub-millisecond, right? So it's less than a millisecond. And then for the thin edge, what we're talking about is, again, latency is in milliseconds all the way through this, except for the cloud where that could be in the seconds range. But for the thin edge, where I say it's low latency, that is typically still, probably less than 5 milliseconds. And then the thick edge, we're talking latency there between 10 and 100 milliseconds. And then with the cloud, it's much higher there. I don't know if that answers the question.
Very good. Okay, is there a use case where cloud computing is better than edge computing? It's a good question.
Yeah, that is a good question. It really does depend on the application. Clearly both have got their own use cases. I think it's almost a combination. You need both. But where cloud computing is very useful is if you've got high amounts of disparate data from lots of different sources that need to be analyzed to provide sort of an overview. So a really good example of that would be you kind of need the edge as well. So you need the edge computing capabilities, but where the cloud would absolutely be required is traffic analysis. And that's a good example there. So if you think about it, you've got sort of localized traffic analysis, regional within small cities or hubs. But if you want to get that overall picture, the only way to do that is to have a cloud system where all of the regional centers, all of the localized edge computing devices can send their data, and then that'll give you that overall picture.
Very good. Here's one. Is there any plan from ProSoft for having a special gateway where we can include a third-party edge computation software solution?
Newton, that's a great question. Yes, that is something that we are working towards. If you can please share your details, then I would be happy to connect with you and discuss further about where ProSoft is heading in that direction. So I wanted to ensure that today's education is more educational, and hence that's why I did not talk about anything specific to ProSoft, but I would be more than happy to connect with you and answer that question in more detail.
Very good. Give it a few more seconds here. Let's see. How does IT/OT convergence affect edge computing?
Another good question. Again, like I was explaining through the presentation, it's almost a mandatory requirement, this IT/OT convergence, before you can do edge computing, because if you look at even this slide, or you look at the evolution and sort of all of the drivers that are driving this edge thing, it's a combination of OT and IT skill set that's required, right? OT is obviously extremely strong in process control, industrial protocols, understanding how machines work, but then you've got this IT skill set that's coming in that's all about understanding how containers work and how virtualization works, and how app orchestration. So the ability to run multiple containers, for example, and managing all of those containers. So without this IT/OT convergence, without this collaboration between the two, an edge computing project is not likely going to be successful. So it's very, very important to ensure that both organizations are very involved in any edge computing type of application.
All right. Let's give it a few more seconds, see if there's any more questions. Okay. Well, very good. Looks like we went 10 minutes over, which is fine because we had some questions. But thank you guys very much for joining. We will again check your inbox for the presentation and the recording of this video. And Vishal, great job. Thanks very much.
Thank you, everyone. Thank you for your time today. Talk to you all soon.